Okay, the next unit that we're going to be starting up and try and finish before Christmas break is thermodynamics. Thermodynamics is the relationship between chemical reactions and heat. We're going to talk about what causes chemical reactions to occur and the concepts that are mostly through this unit: enthalpy, entropy, and Gibbs free energy. Okay, two vocabulary terms that you need to be familiar with are system and surroundings. System is the actual chemical reaction that is taking place. Surroundings is everything around it. If you'll remember when I took the hydrogen and oxygen balloon and we set it on fire to produce water, anything inside of that balloon is considered the system. The balloon and everything around it was considered the surroundings. So heat flows into the system from the surroundings is called an endothermic process. For example, if I have ice, in order for ice to melt into liquid water, I have to add heat from the surroundings to the system. The products, the ice, actually the liquid water, therefore are at a higher energy than the reactants were, as they have absorbed this energy right here. So now they have more energy. This is called endothermic. Exothermic is when the heat flows out of the system to the surroundings. So if you burn methane like in a Bunsen burner, and you're burning that methane, all that heat is released to the surroundings. That's called exothermic. The products, in this case, contain less energy than the reactants, as energy has been released. The enthalpy of the reaction, this delta H, that H stands for enthalpy. You could think of it as heat if you would like to. The heat that is released or absorbed in a chemical reaction is equal to this equation. The change in heat is equal to the enthalpy of the products minus the enthalpy of the reactants. However much energy the reactants had over here is subtracted from the products. So the heat released or absorbed in the reaction is your delta H. The heat contained within the products minus the heat contained within the reactants. For example, I've got these two reactions right here. Hydrogen plus oxygen produces water. That's what we had in the balloon. Okay? This is what we had in the balloon. Then we provided a little bit of a spark. It produced water. Okay? And it also released 572 kilojoules of energy. So that negative symbol right there means that it was exothermic. Therefore, if I take this reaction and flip it, then every exothermic reaction's opposite is going to be endothermic. This reaction requires heat. It requires energy for water to break down into hydrogen and oxygen gas. So if I was looking at an energy diagram, the reactants right over here would have more energy than my products. So here's the balloon right here. I provide that little bit of activation energy, and it releases all of this energy to produce water. So it's negative 572. If I take water, I would have to add energy to it to get all the way up to here to produce hydrogen gas and oxygen gas. That would be endothermic. We're going to be using words like heat and temperature. They are different. Heat is a form of energy that's measured in joules. It's also measured in calories. We'll get to that in a second. Temperature is the measurement of how fast the molecules in a chemical reaction are moving. Okay, so it's the average, it's the measurement of the average kinetic energy, or how fast they're moving, in a system. And it's measured in Kelvin. You guys are familiar with Kelvin. There's 4 methods for finding delta H. We're just going to go over the first one today, measuring it using a calorimeter. Calorimetry is the measurement of heat flow from a colder object to a hotter object. We're going to use something called a calorimeter. It's the device that is used to measure the heat flow. You can't directly measure heat flow, but you can measure parts that add up to heat flow. And it's this equation right here, what I like to call Q equals MCAT. Okay? Q is going to be the heat, lost or gained. M is the mass of, typically in a calorimeter we use water. C is the specific heat of water. And delta T is my change in the temperature. Okay, usually in calorimetry you have a coffee cup. That's going to be your calorimeter. You put water in it, and then you add something to it, add something to the water that's going to make the temperature of the water either go up or go down. Okay? The specific heat for water is 4.184. That's a large number, which means it takes a lot of heat to increase the temperature of water. Iron specific heat is 0.84, which means it doesn't take as much heat to raise the temperature of iron. So this is the coffee cup, and you typically put water in there, and this is going to be our thermometer taking the temperature, and then whatever you add to the system, okay, the temperature is either going to go up or go down, and therefore we can solve for delta Q. When measuring the heat lost or gained in the reaction that takes place in a coffee cup calorimeter, we're going to use water. So that means that this C right here is going to be 4.184, which is the specific heat of water. This is going to be the mass of water. This will be just the change in temperature of water. And then you can solve for Q. The heat lost or gained by the water is equal to, but opposite in sign to the heat lost or gained in the reaction. Okay? The amount of heat that the water gains is equal to the amount of heat that was lost by whatever it is that you put in the calorimeter. So for example, if you calculated delta Q for water to be 568 joules, the water gained heat. This means that it is an exothermic reaction that gave off heat to the water, as the heat gained by the water is equal to the heat lost by the reaction. So therefore delta Q for the reaction is negative 568. So the reaction gives off that heat, the water gains that heat. Okay. So if I take 0.075 moles of HCl and 0.075 moles of sodium hydroxide and I add them to 150 milliliters, which is the same thing as 150 grams of water, in a coffee cup calorimeter, the temperature of the solution increases from 23 to 29.9 degrees Celsius. Calculate the enthalpy change for the formation of 1 mole of water. Assume that no heat is lost for the surroundings. Well, the first thing we're going to do is solve for Q. And we're going to do Q equals MCAT. Okay? The mass of my water, remember the density of water is 1 gram per milliliter. So 150 milliliters of water is 150 grams of water. The specific heat of water is 4.184. The change in temperature went from 23 up to 29.9, so that's roughly 6.9. Multiply all this, and you'll get an answer of 4,330 joules. That's the amount of heat that the water gained. Okay? So what's the delta Q for the reaction? Well, it's going to be the same number, because the heat that was lost is equal to the heat that was gained. The heat gained by the water is equal to the heat lost. Therefore, this reaction is exothermic because the system lost heat. The water is part of the surroundings. It gained heat. So therefore, it's going to be the same value, 4,330 joules, just a negative number. Okay, so to find the delta H, you're going to take your joules and you're going to divide it by your number of moles of water that you produced. Remember, we used 0.075 moles of hydrogen, 0.075 moles of hydroxide, so we produced 0.075 moles of water. So you take your heat, your Q, and you divide it by the number of moles produced. And that's in joules. It's still negative, exothermic, and that's such a large number that we tend to use kilojoules, so we're going to move the decimal over 3 places, to negative 58 kilojoules. So what's the difference between delta Q and delta H? Delta Q is the heat lost or gained in the experiment that took place in the calorimeter. Okay, so it's the heat lost or gained. Delta H, or delta enthalpy, is the heat lost or gained in the balanced chemical equation. And usually it's divided by moles. This would just be joules. This is usually kilojoules per mole.